Resistors in direct series can be combined by adding them together directly. You can combine any number of resistors that are directly in series this way. What do I mean by combine resistors? I mean that you can model a direct series of resistors as one single resistor that has the same effect on the voltage and current as the resistors that were in series combined. That means we can rewrite the left circuit as the right circuit here. R1 plus R2 plus R3 is the combined resistor, and it has the same effect on the current through the circuit as the three resistors combined did. I will now explain why we can combine resistors in this way. Recall two helpful notes. Number one, the voltage drop across all three of these resistors in total is 12 volts. This should make sense because particles that are accelerated with 12 volts of energy in this battery need to use up all those 12 volts before they go to the bottom of the battery again. Secondly, these resistors are directly in series, which means the same current must be traveling through every single one of those resistors. Let's say we don't know what that current is. We can describe that current as I. Let's also say we don't know the voltage across the resistors combined. We will just call it V. Could we still combine these resistors? Let's say each resistor has a voltage drop across it. R1 gets V1, R2 gets V2, R3 gets V3. Based on Ohm's law, we know that V1 equals I times R1, and V2 equals I times R2, and V3 equals I times R3. What this is basically saying is that the amount of voltage that each resistor drops the circuit by is basically proportional to the resistance. The greater the resistance, the more the voltage drop. And since the current is the same through every resistor, the resistors' proportion to each other describes the proportion of their voltage drops to each other. That is that if R3 is twice as big as R2, then its voltage drop for a given current must be twice as big as the voltage drop for R2. Now, our goal in creating an equivalent resistor is to have a single resistor that replicates the entire series of voltage drops. So we don't have to have three, we can just have one. So let's sum together these three voltage drops, V1, V2, and V3, to get the total voltage drop across the entire set of resistors. If we had a secret equivalent resistor that could make this total voltage drop, we could describe the total voltage drop as the current times the equivalent resistor Req. So this is our imaginary resistor that is equivalent to the effect of R1, R2, and R3. It's equivalent because given a current, it has the same effect on the voltage as all three resistors do. All three resistors' voltages must sum to the voltage created by this equivalent resistor. If we plug in for every voltage the Ohm's law version of that voltage, we can see that the equation is as follows, and we can cancel out every I to get the simple equation R1 plus R2 plus R3 equals R equivalent. And this works for any number of series resistors. So basically what we're saying is that because the current through a bunch of series resistors is the same, their effect on the voltage can be added up directly, because each resistor's individual effect on the voltage is proportional to its resistance. Or the same magnitude of current through a bunch of resistors results in proportional magnitudes of voltage drop that we can then add together directly. In the left circuit, R1 and R2 are in series, but they are not in series with R3 or R4 because at the end of R2 you can go in either of two directions. R1 and R2 can be combined, but they cannot be combined directly with R3 and R4. Let us say you wanted to determine the voltage across this 3 ohm resistor. If we had the current across this 3 ohm resistor, we could multiply that current by the resistance to get the voltage drop, but we don't currently have the current. One way that we could get the current. We can simplify this circuit by adding together all of the resistors in series. 3 plus 3 plus 6 is simply a 12 ohm resistor. This 12 ohm resistor acts the same as these 3 resistors. And we can clearly see that because there is a 12 voltage drop across this 12 ohm resistor, there must be 1 amp of current in the circuit because I equals V over R. Now that we have combined the resistors to determine the current in the circuit, we can decompose the resistors and go backward. So we can rewrite this circuit in the old way, 3 ohms, 6 ohms, 3 ohms, but with the added knowledge that the current through these 3 resistors is 1 amp. Thus, we can determine the voltage drop across this 3 ohm resistor by multiplying its resistance by its current, and we get 3 volt drop. Another expression of the facts that we've just discussed is something called the voltage divider. If you know the total voltage across a series of resistors V, you can determine the voltage across a single one of those resistors by figuring out the ratio of that resistor to all of the resistors. The ratio of R1 to the total resistance is R1 over R1 plus R2 plus R3. This ratio describes how much of the total voltage drop R1 experiences. So if we simply multiply this by V, we get V1. So if you have n resistors in series with voltage V across them, the voltage Vm for the mth resistor is equal to the total voltage times the ratio of the mth resistor to the total resistors. Take a minute to chew on this equation and try and express it in your own words. This concludes our lecture on equivalent resistors in series.